Okay, guys and gals, in this video we are going to do sections 2.8 and 2.9 and wrap up chapter 2. So in 2.8 we are going to look at one of the bigger application sections in this class, which is called related rates. So this is going to kind of combine the implicit idea that we learned in the previous video to word problems and show you kind of how that works, and we'll do a few examples along the way. So first off, what is a related rate problem? So let me kind of read through this for you. In related rate problems, we try to compute the rate of change of one quantity in terms of the rate of change of another quantity, which may be more easily measured. So to find the equation that relates the two quantities, we use the chain rule, which it's kind of weird there how they say the chain rule. I'll explain that when we do our first example. But the big thing is you are going to differentiate everything with respect to time. So that means if you think back to the implicit section, when we took the derivative of y, I told you that you had to put a dy dx term. Well, that only counted for y's. In this section, any letter that you see, whether it be X or Y, I think we might see some R's a little bit and other letters, but no matter what letter it is, every time you take the derivative of a particular letter in this section, you have to put a implicit term, but since we're doing it with respect to t, you'll have things like dx dt and dy dt. So you're going to have a lot of terms here. Now, only one of these you're going to be solving for. The rest of them you'll be given in the problem, and you'll just plug in and do a little bit of arithmetic. So we'll see that in all the examples today. So let's start off with the first one. Example number 1. A cylindrical tank with radius 5 meters is being filled with water at a rate of 3 cubic meters per minute. How fast is the height of the water increasing? So I gave ourselves a little bit of a diagram here so we could see that as well. So what I usually do on these related rate problems is that I start with the picture and I kind of label what I can, and then we'll kind of develop a formula for you. So it says that we have a cylindrical tank with radius r, or radius 5, sorry, so what's also r. So we know that the radius of this cylinder is r, which is equal to 5. It's being filled with water at a rate of 3 cubic meters per minute. So when you see that cubic unit, that's volume. But since this is a rate of change, we don't call this V. This is what I was talking about a minute ago. Rates of change in this section are denoted as the derivative of that unit, so the derivative of volume, which is dV, over with respect to time, so that would be 3. It's asking how fast is the height of the water increasing, so what is this rate of change? So since we're trying to measure what height is, I want to know what is dH dt. Well, that's the unknown. Now, since we are given the rate of change of the volume of a cylinder, this is where your geometry skills are going to come into play. You have to now remember what is the volume formula for a cylinder. So as we go through these today, make sure you note them down if you don't remember some of these formulas. So the volume of a cylinder is pi r squared h. Now, we're going to eventually take the derivative of this, but before you do that, I always recommend you try to plug in numbers that will not change. So while the volume is changing and the height is changing, the radius of the cylinder never changes. It's going to be 5, whether you're at the bottom, the top, or anywhere in the middle. So any fixed numbers, such as this 5, you are allowed to go ahead and plug in. So I can say that the volume of this cylinder is pi times 5 squared times h, which is the same thing as volume, equals 25 pi times h. 25 pi is just a constant. H and v are your variables here. So going back to section 2.6, when we did implicit derivatives, I'm going to start from the left and take the derivative of everything. The derivative of v, while it is just 1, since we're doing implicit, you have to call that dv dt. 25 pi is just a constant, and the derivative of h is 1, but as I said, once again, you have to put the implicit term, which is dh dt. That's it. This is related rates. Your job now is, since we're looking for dh dt, you should know every other value. We know that dv dt is 3, so 3 equals 25 pi times dh dt, And if you divide both sides by 25 pi, you can say that 3 over 25 pi is equal to dh dt. That is the rate in which the height is increasing as you are pumping this water in. And that's it. But that is the idea of related rates. So we're going to have a formula. We're going to have a lot of variables and unknowns. Your job is to plug in what you know and solve for the unknown the question's asking for. So very good. That's what we're going to work on in this first section. All right, so let's change up the geometric formula. How about number 2? If a snowball melts so that its surface area decreases at a rate of 1 square centimeter per minute, find the rate at which the diameter decreases when the diameter is 10 centimeters. All right, so while I did not give you a picture this time, that's fine. We're going to have to actually assume something for a second. I'm going to assume that we are all perfect snowball makers, and we are going to make a snowball that is a perfect sphere, because if not, this problem is way harder than it needs to be. So we're going to assume it's a perfect sphere. So what do we know? Let's kind of read the problem here. If a snowball melts so that its surface area decreases at a rate, so we know that the surface area, which is dA dt, is getting smaller. That's a key thing here. Since it's decreasing, that's going to be our 1. Oops, sorry, I didn't mean to put the C there. I'll put the variables later if you need to, but the 1 is what you're focused on. All right, it says find the rate at which the diameter decreases, so we're going to call that dd dt, that's our unknown, when the diameter is 10 centimeters. All right, so if we know the rate the area is changing, what is the rate of the diameter changing when the diameter hits exactly 10 centimeters? So back to geometry now. What is the formula since we know area? What is the formula of the surface area of a sphere? So if you don't remember it, the surface area of a sphere is 4 pi r squared. Now in this case, A and R, there's a problem. A is not constant, so don't plug that in, and don't assume R is constant. Since the formula in geometry is given in R, but they want us to relate this to diameter, we have to do a little bit of arithmetic here. So remember what that means. We know that diameter is the same thing as double the radius. I need to get rid of this R in this formula. So I'm going to get the R by itself over here on the right. So that is D over 2 equals R. And I'm going to substitute that directly into my formula. So I can say that surface area is equal to 4 pi times D over 2 squared. Then I'm going to do a little bit of algebra. Surface area is now equal to 4 pi times D squared over 4. And as you can see very nicely, the 4's cancel. And I can now say that a different formula for surface area is pi d squared. That's it. Now, neither A or D is constant. They are both changing throughout the entire process, so you're not going to plug any constants in. Instead, going back to my red pen, I'm going to go ahead and take the derivative implicitly of this formula. So the derivative of A is dA dt. Pi is just a constant. Actually, we'll put it right here, pi. And the derivative of d squared is 2d times the implicit term, which is dd dt. Now plug in what you know. We know that dA dt is 1. We know that 2 times pi is just 2 pi. The diameter at this point is 10, and our unknown is dd dt. All right, from here it's just algebra. So this is 1 equals 20 pi times dd dt. And if you divide both sides by that 20 pi, you can say that the rate that the diameter is changing is 1 over 20 pi. That is your answer to this problem. So as you can see, the actual calculus is not too difficult here. It's just making sure you get everything labeled correctly and making sure you have the right variables before you start taking derivatives. Very good. All right, so let's change another geometry. I'm trying to get all the geometry formulas you might see on your homework and your quizzes. The height of a triangle is increasing at a rate of 1 centimeter per minute while the area of the triangle is increasing at a rate of 2 centimeters squared per minute. At what rate is the base of the triangle changing when the height is 10 centimeters and the area is 100 squared centimeters? All right, you have a lot of stuff going on here, so let's take our time here. Essentially, we know from the top, the height of the triangle is increasing at a rate. So the height is changing. That's going to be, according to us, dh dt is 1. The area of the triangle is also changing. So that is dA dt, which is going to be 2 according to the problem. So then it says, at what rate is the base of the triangle changing? So we don't know dB dt. That's unknown. But what we do know is that the height is equal to 10 and the area is 100. So since the rate of change that they gave us is the area, we have to start with area of a triangle. So back in geometry, a little bit easier formula hopefully to remember is that area is 1/2 base times height. Now, we know base and height are the correct formulas because you see we have a dH dt, a dB dt, all that stuff's given. So you don't have to change anything. You just have to now take the derivative of this. But when you go to do that, notice that there is a problem. The derivative of A, that's not the problem. That's just dA dt. But on the right-hand side, you've got, for the first time, two variables being multiplied together, a 1/2 b and an h. Since we had to take the derivative of all of this, you have to now do the product rule like we did back in section 2.6. So if I do the product rule here, it will be f, which is 1/2 b, times the derivative of h, which is dh dt, plus h times the derivative of 1/2 b, which is 1/2 dB dt. That's it. That's the calculus step. You now got to plug all your information in. dA dt is going to be 2 equals 1/2 the base. Aha, so here's your problem. Sometimes when you're working these problems, you may not know all the information. Well, that's okay. I got to figure out what b is. So way over here. Remember, you told me that the area of a triangle is 1/2 base times height. Well, since we know what the height and the area are at this time, we can figure out what the base is. So area is 100 equals 1/2. We don't know the base, but the height is 10. Well, half of 10 is going to be 5, so that is 100 equals 5b. And if you divide both sides by 5, we can say that b is 20. So back to my formula, I can say that b is 20. We know that dH dt is 1 plus h is 10 times half of, here's the one we've got to find. We're looking for dB dt. All right, so clean this up a little bit. So this is 2 equals half of 20 times 1 is 10 plus half of 10 is 5, still being multiplied by the dB dt. Subtract the 10 over, so that's -8 equals 5 dB dt. And then divide both sides by 5, and we can say that dB dt is -8/5. Now you'll notice back in the problem, it did not tell us whether or not the base was increasing or decreasing up front. We had to figure that out ourselves. But since dB dt is a negative number in this process, that is a way that we can double check that this value is decreasing. So while the height and the area are getting bigger, we can see that the base is actually getting smaller. All right, so like I said, keep going. Example number 4. A boat is pulled into a dock by a rope attached to the bow of the boat and passing through a pulley on the dock that is 1 meter higher than the bow of the boat. If the rope is being pulled in at a rate of 1 meter per second, how fast is the boat approaching the dock when it is 8 meters from the dock? All right, so this time I went ahead and gave you the picture out of the textbook because like I said, I can't draw this very well, but essentially let's use this picture to label what we have. A rope a boat, is being pulled into a dock by a rope attached to the bow of the boat and passing through a pulley on the dock that is 1 meter higher. So, according to this, if we were to draw a straight horizontal line from the bow of the boat to the dock, it is saying that this pulley is 1 meter higher. Okay, that's fine. We'll label that. If the rope is being pulled in at a rate of 1 meter per second, now you'll see that this actually forms a right triangle. So what I'm actually going to do is I'm going to call this X, Y, and R to form my right triangle, just so I have something to label here. So if the rope is being pulled in, so the rope is our R value, that means that the rope, which is dr dt, is going to equal 1. It's asking how fast is the boat approaching the dock. So how fast, so the boat's going along this x-axis. It's asking what is the rate that dx dt is changing when we know that x is 8. So when x gets to 8, what is the rate that x is changing? All right, so now in this case, they didn't give us area or anything, so we're not going to do area of a triangle. Instead, since there is a right triangle, my suggestion is if you're doing a right triangle and not doing area or volume or any of that stuff, I would go with Pythagorean's theorem. So we know that based on this formula, Pythagorean's theorem is x squared plus y squared equals r squared. All right, so in this case, are any of those numbers fixed, which means they don't move? Well, one of them is. Your y is never going to change. The height of the dock as your boat comes across is not going to change the height. So I know that y is going to always be 1. So if I plug that in, I know that x squared plus 1 equals r squared. Now we move into the calculus part. If this is your formula, take the derivative of this implicitly. So the derivative of x is 2x, but you have to put the dx dt. The derivative of 1 is 0, so I'm kind of glad that that number is fixed. It goes away, equals the derivative of r squared is 2r times dr dt. Now pay attention, and something I meant to mention on the last problem, but I'll go ahead and mention it now. Go ahead and double check if you'd like, if you know all these numbers. Do you know what x is? Yes, we know it's 8. Do we know dx dt? No, because that's what we're looking for. Do we know r? No. We know dr dt, but we do not know what r is. So what you have to do is kind of like the area of the triangle problem is back over here on the right. I'll do this in blue. Since we know that Pythagorean's theorem, x squared plus y squared equals r squared, plug in what you know. Well, we know that x is 8. We know that y is always 1. The question is, what is r at this value? So that would be 64 plus 1 is 65, which equals r squared. And if you take the square root of both sides, you can say that r is root 65. Now we know enough to solve this problem, so let's plug in all the numbers that we know. This would be 2 times 8 times dx dt equals 2 times the square root of 65 times dr dt, which is 1. All right, so this would be 16 dx dt equals 2 square roots of 65. Divide both sides by 16. So dx dt is 2 square roots of 65 all over 16. And I do need you to reduce this for me as well. The 2 and the 16 both share a 2 in common. So we can say that dx dt is equal to the square root of 65 divided by 8. So that means that is the rate at which your boat is moving when you hit that 8 meter mark on the x-axis. And there's an example of where you can use Pythagorean's theorem. We'll see another one of these in a minute on what I call the ladder problem, and you'll see it right away when we get there. All right, so the next two problems that I'm going to show y'all are probably the two that students have the most trouble with, so let's make sure we get these down. And after that one, then we'll get to that ladder problem I was mentioning. So it says gravel is being dumped from a conveyor belt at a rate of 30 cubic feet per minute, and its coarseness is such that it forms a pile in the shape of a cone whose base diameter and height are always equal. How fast is the height of the pile increasing when the pile gets to be 10 feet tall? All right, so when I read this, the first thing I see in that before the first comma, gravel is being dumped from a conveyor belt at a rate of 30 cubic, that's the key word, cubic feet per minute. So I know that the rate that the volume is changing is going to be 30. Now here's the trick. Its coarseness is such that it forms a pile in the shape of a cone. Okay, we'll get to the cone in a minute, but the key is right here. The base diameter and the height are always equal. So I know that the diameter and the height have to always be the same thing, but that's going to play a role in a minute. How fast is the height of the pile increasing? So that is dH dt is unknown when you know that the height becomes 10. All right, since we're dealing with volume of a cone, you have to remember your volume of a cone formula. So volume of a cone is 1/3 pi r squared h. Now you'll notice here's the problem. There's an r in this formula and there's nothing to do with radius over here. That's fine. That's where that's where this relationship right here is going to come into play. So since I know that diameter and height are the same thing, I need to use r though. There's no diameter. So what from earlier today, know that diameter is 2 times r. And to get r by itself, if I divide both sides by 2, I can say that the radius is always equal to half the height. If I substitute this into my volume formula, I can say that volume is 1/3 pi times h over 2 squared times another h. So volume is 1/3 pi times h squared over 4 times that other h. And if I put all of my like terms together here, the 3 and the 4 on the bottom make this a 1/12 pi, and h squared times h is h cubed. So this is our volume formula. We've done all of our relationships. So if I take this formula, notice that there's only a v and an h. That's good. That's the only rates of change we have. So I can now take the derivative of this implicitly. So I can say, and I'll move over here to the left out of the way, dv dt is equal to 1/12 pi. The derivative of h cubed is 3h squared times dh dt. Start plugging in what you know. We know that dv dt is 30. 3 times 1/12 actually makes this a 1/4 pi. We know that h is 10, and we're going to square that, and then dh dt is our unknown. Let's see, this becomes 30 equals 10 squared is 100. 100 times a fourth is going to be 25 pi dh dt. And then dividing both sides by 25 pi, I'll come up here, says that dh dt is equal to 30 over 25 pi. So it makes sense that the height of this pile is getting higher as you dump more and more sand on it. Now you may think that wasn't too bad, but remember the trick is that blue circle at the top. Noticing that relationship and noticing that there is no diameter and turning it into radius is the trick in this problem. So just be careful. I've had a lot of students get confused on this particular problem, so I wanted to make sure I worked it out for you on the video. The second one that I've seen students get messed up on a little bit is this problem. And while it doesn't seem too bad because it's only 2.5 lines on your screen, it's just because it's going to make you know some trig, and you're going to have to also be okay with ugly numbers for a few seconds because there's going to be some ugly numbers that I can't fix until the very end. And that's fine. We'll deal with it together. So here we go. It says a kite 100 feet above the ground moves horizontally at a speed of 4 feet per second. At what rate is the angle between the string and the horizontal decreasing when a 200 feet of string has been let out? So essentially, here's what this is saying. You have a kite that we know is 100 feet above the ground. But you know that every kite has a string. So we're going to assume the string goes in this direction. So you assume that some person's holding the string. And what the trick is that this does form a right triangle. Now let's go back and read everything. The kite 100 feet above the ground moves horizontally at a speed of 4 feet per second. So kind of like the boat problem earlier. If I call this x, this y, and this r, I can say that dx dt is changing at a rate of 4 feet per second. At what angle between the string and the horizontal? So the angle theta is right here. At what rate is the angle changing? So for the first time, we're going to have to figure out what is d theta dt when 200 feet of string is left out. So r equals 200. So now there's many ways to probably tackle this problem. It's going to be more of you pick your trig function you want to do and go with it. Just looking at this, since I know what y is, this 100 feet, this kite's not going to change. The height of the kite's not changing. It's because the kite's moving horizontally. Since I know y doesn't change and it's fixed, I'm going to use y. And since looking at my information, since I know dx dt and that's my adjacent, what I'm actually going to prefer to do here is I'm going to say that tangent theta is the better trig function to use. Anytime you're looking for the rate and angle is changing, you're going to have to use one of the 6 trig functions. I just say pick one that you think works the best, go with it. The worst that's going to happen is it doesn't work and you got to start over, which does happen from time to time. Just be ready for that. So I know that tangent theta is your opposite, which is y, over your adjacent, which is x. Now, since y doesn't change, I'm going to go ahead and plug that in. I can say that tangent theta is equal to 100 over x. And if I multiply both sides by x, I can say that x times tangent theta is equal to 100. All right, fantastic here. So what I'm actually going to do is I'm going to make life a whole lot easier here. I just realized while I'm working this problem, there's actually a better way to do this. So let me pause. It's only one line, so I apologize if you need to back up a little bit. Let's actually go to right here. I don't like the x on the bottom, so we know a trig way that you can flip that over. So why don't we change our trig function? Oops, don't want that. Oh man, I erased it. That's actually probably better that I erased it anyways, because I can start over here. So in this case, let me kind of redraw that. I hit the wrong button. We know that y is 100. We know x. We know r. We know that dx dt is 4. We don't know what d theta dt is, but we know r is 200. And what I had gotten to the point of saying is that I'm having trouble this morning. We have gotten to the point of saying that tangent theta is equal to 100 over x. And what I was trying to say before I hit the all clear button by accident is that if I want to flip this fraction over, that's fine. Just change your trig function. I know that tangent theta can be flipped into cotangent theta, and this is the same thing as x over 100. So now it's a little bit easier, because now when I multiply both sides by 100 instead, I can say that 100 cotangent theta is equal to x. Now I'm going to take my derivative. 100 is just a constant. From the trig section, the derivative of cotangent is negative cosecant squared theta. But since we're doing related rates, you have to pick up the d theta dt term. And this equals the derivative of x is just dx dt. All right, so now plug in what you know. The problem is going to be is that do you know what cosecant is? And I believe we actually do here. That's actually a good thing. So this is negative 100 times cosecant squared. So cosecant is the reciprocal of sine. Since we know that sine is opposite over hypotenuse, cosecant would be hypotenuse over opposite. The hypotenuse is r, which we know is 200, and the opposite is y, which we know is 100. That's actually really, really nice. We don't know d theta dt. That's the whole point of this problem. But we do know that dx dt is 4. All right, do a little bit of arithmetic here. So this would be negative 100 times 200 divided by 100 is 2, and 2 squared is 4. This is going to give me negative 400 d theta dt is equal to 4. And then coming up here, so it's a little bit easier to write, I can now say by dividing both sides by negative 400 that d theta dt is 4 over negative 400, which is the ratio of negative 1 over 100. So this says that your angle is getting smaller, and that makes sense. As your kite is going to the right, this angle theta down here should be getting smaller and smaller because your string is being stretched out further away from the person that's holding it. So, very good. All right, so now we're on to that ladder problem. So I believe this is going to wrap up this first section, unless I'm forgetting about a problem that I put in here. But example number 7, it says a ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Then a part B, how fast is the angle between the ground and the ladder changing? So there's a lot of information, and it can be really confusing if you just, like I said, I'm going to draw myself a picture here. So let's assume we have a wall, and obviously there's a ground next to it. So let's say that we have a ladder leaning against the wall. You see kind of form that right triangle here. So we're going to once again call this X, Y, and R. I know that R is 10 because it says that ladder, which is the R side, is going to be 10 feet long. If the bottom of the ladder slides away from the wall, so that's this part right here, if dx dt slides away at 1 foot per second, how fast is the top of the ladder sliding down the wall? So dy dt is unknown when the bottom of the ladder is 6 feet. So when x is 6. Now, before I go on to the angle part, we don't need any trig for this first part. Since we're not doing any angles, we can actually go back and use Pythagorean's theorem. So I can say that x squared plus y squared is r squared, back like the boat problem. Look for your fixed values. Your ladder length is never going to change. While that ladder falls down the wall, the 10 feet is not going to change. So I'm actually going to plug the r equals 10 directly in. So that would be x squared plus y squared equals 10 squared, which is 100. Now I'm going to take the derivative. The derivative of x squared is 2x dx dt plus y squared, which is 2y dy dt. And since 100 is fixed, the derivative of a constant is going to be 0. Now, do you know all the information? Let's see. From left to right, x is 6. We know that. dx dt is 1. We're looking for dy dt. The problem is that you don't know what y is. So we're going to have to go back and do a little bit of work. We know, once again, back to Pythagorean's theorem. X squared plus y squared is r squared. We know x is 6. Y is unknown, but r is 10. That is 36 plus y squared equals 100. So y squared would equal 100 minus 36, which is a very nice number of 64. So we can see that y is actually 8. Good. So we found the number we need. Go back to your red part and let's plug in what we know. This would be 2 times 6 times 1, because we know all those numbers, plus 2 times 8 times dy dt equals 0. Simplifying this is going to actually give us 12 plus 16 dy dt equals 0. Subtract the 12 over, so 16 dy dt is going to be negative 12. And then if you divide both sides by 16, dy dt would be negative 12 over 16. But since both of those share a 4 in common, that does simplify into negative 3/4. That is your first answer. I'm going to kind of block this part, all this stuff off, just so I kind of have some more room. All right, so that makes sense. You got dy dt is negative because your ladder is falling down the wall. Part B says, how fast is the angle between the ground and the ladder changing? So ground and ladder, that would be the lower right-hand side, that's theta. And once again, since you have all your information, it doesn't really matter what trig function you pick. Pick whatever one you want to. Just out of curiosity, I'm going to do sine. So I'm going to say that sine of theta is my opposite, which is y, over my hypotenuse, which is r. Now, once again, I know that r never changes, so I'm allowed to go ahead and plug in the number that r is represented by, which is 10. So I can say that sine of theta is y over 10, and then multiplying both sides by 10, oops, I don't know why I wrote cosine for, but you should get 10 sine theta equals y. Now you can do your implicit term, so take the derivative of everything. 10 stays the same. The derivative of sine, this is probably why I did it, derivative of sine is cosine theta. Don't forget the implicit term, which is d theta dt, equals the derivative of y, which is dy dt. So in this case, we would say that 10 multiplied by cosine, which is your adjacent over your hypotenuse. The adjacent of theta is x, which we know is 6, and the hypotenuse is r, which we know is 10. We don't know d theta dt, and we just actually found dy dt to be negative 3/4. As you can see, the 10s cancel, so you're left with 6 d theta dt equals negative 3/4. And if you divide both sides by 6 here, you should get that d theta dt is negative 3 over 24, which both of those share a 3 in common, and that becomes negative 1/8. Once again, that confirms to us that the angle between the ladder and the floor is getting smaller, which makes sense if the bottom of the ladder is sliding away from the vertical wall. Very good. Oh, there is another problem. Sorry. So one more ladder problem. So last problem for related rates, and then we'll move into a lot shorter section to wrap up this video. So example number 8. The top of a ladder slides down a vertical wall at a rate of 0.15 meters per second. At the moment when the bottom of the ladder is 3 meters from the wall, it slides away from the wall at a rate of 0.2 meters per second. The question is, how long is that ladder? This is going to look very similar, so I'm going to draw this a little bit quicker this time. You have your vertical wall and you have your horizontal, and we have our ladder again. So in this case, it says, so we have, let's see, let me label it X, Y, and R. The top of the ladder slides down a vertical wall at a rate of 0.15 meters per second. Now the reason I did the first ladder problem was to show you that when you are sliding down the wall, it makes sense that I can call this negative 0.15, not positive. We saw that on the last problem. At the moment when the bottom of the ladder is 3 meters from the wall, so it's saying when X is equal to 3, it is sliding away from the wall at a rate of 0.2. So that's going to stay positive. We saw that on the last one. dx dt is 0.2. The question is, how long's the ladder? Well, once again, I am going to start with Pythagorean's theorem here. Like I said, and from there we can kind of venture around and figure out what to do. But In this case, I'm going to say that x squared plus y squared is r squared. So since we know that r is fixed in this case, I know that even though I don't know the number, when I take the derivative of this, it's going to end up going to 0. Once again, this is a constant. So when I take the derivative, you can say that 2x dx dt plus 2y dy dt is equal to 0. Plugging in what you know, we know that 2 times 3 times dx dt, which is 0.2, plus 2 times y times dy dt is negative 0.15 is 0. Now you're thinking, I know you're probably thinking, I thought we were looking for r. Why are we going to solve for y? Well, the question is, you can't actually get r until you know both x and y. And I didn't give you y in this problem, so you'll have to figure that out before you can find r. So that's okay. 2 times 3 times 0.2, if you need to use your calculator, that's fine. That's going to be 1.2. 2 times negative 0.15 is negative 0.3y equals 0. Subtract the 1.2 over, so that's negative 0.3y equals negative 1.2. And then dividing, that is ugly, whatever that is, so we'll try to fix it. So y is going to equal 4. And now that you know that y is 4, go back to your original Pythagorean theorem, and you can now plug your x and y into there without using calculus and figure out r. So 3 squared plus 4 squared is r squared. That's 9 plus 16 is 25 equals r squared. So we have just found that the length of this ladder is 5 meters long. All right, so that wraps up section 2.8. That's not the end of the video, though. So what we're going to do now is we're going to move into a lot smaller section, which is not a very big section, but it's something we have to talk about a little bit. And that is the idea of linear approximation and differentials. So section 2.9, this is going to wrap up chapter 2, and in the next video, we'll start chapter 3. All right, so what linear approximation is a formula so that you can approximate any function that's out there at any value. Now, the reason this is not as popular anymore is because nowadays you have a calculator, but remember, after you go on, some classes don't allow you to use a calculator, so sometimes you have to be able to approximate ideas without that. So let me kind of show you what I mean by that. If we know that the linearization formula, or the linear approximation formula, some books call it different things, is formulated by f of a plus f prime of a times x minus a. Well, in example number 1, I think it's the best to see is by example. It says find the linearization of the function at a equals 1, and then use this to approximate the square root of 3.98. So if f of x is root x plus 3, so if you look at your formula, you need two things mainly. You need an f of a and an f prime of a. Well, the easy one's going to be f of a. F of a just means I need to find what is f of 1. That would be the square root of 1 plus 3, which is 2. Then I've got to find the derivative of this and plug the same number in. This would be x plus 3 raised to the 1/2 if I were to rewrite it. So over here on the right, I'll find the derivative. F prime of x, that's going to be chain rule, would be 1/2 times x plus 3 raised to the negative 1/2, technically times a 1. Since the 1 doesn't do anything, I'm going to take this negative exponent and bring it back to the bottom. So that is 1 over 2 times x plus 3 to the positive 1/2, which is the same thing as 1 over 2 times the square root of x plus 3. I know we didn't simplify those a lot on the midterm material, but you'll need to do it a lot more since you're going to be plugging numbers into this. So back to my work, I need f prime of a, which is f prime of 1. So if I plug 1 into that derivative, it would be 1 over 2 times the square root of 1 plus 3, which, doing a little bit of calculation, should give you 1/4. Now I can do my formula. I can say that L of x is equal to f of a, which is 2, plus f prime of a, which is 1/4, times x minus a, which is 1. So technically on your homework, that's all you have to do for your linearization formula. But what they're going to ask you to do now is they want to see if we can use this formula to approximate what the square root of 3.98 is. So in blue here, we're trying to use the function, the square root of x plus 3, to equal the square root of 3.98. The only way that this can be true is if the insides of each radical are the same. So essentially you could drop the radical or square both sides, whatever you want to do, and we could say that x plus 3 is equal to 3.98, and then subtracting the 3 over says that x is 0.98. This is the number you have to plug into your linearization formula. So I can say that L of 0.98 is equal to 2 plus 1/4 times 0.98 minus 1, which is equal to 2 plus 1/4 of negative 0.02. So if you take a fourth of that, this would be 2 minus, and let's see, that would be, like I said, I'm okay with using the calculator right here. That's going to be minus 0.005, which gives us 1.995. And there you go. I'm not going to sweat too much on your assignments. A couple of them are going to ask you to find the decimal approximations, and that's fine. Just do it the same way I did here. But the big thing in this section is that first red box on the left-hand side, the L of x. That's the number you're probably going to be asked to find on your quizzes and such going forward in this class. All right, so let's continue a few more. Like I said, just going to do a few of these to show you how they work, and then I have one little other thing to do, and then we'll wrap this video up. So example number 2 says, find the linearization of the function f of x equals sine of x at a equals pi over 6. So using that same formula, L of x equals f of a plus f prime of a all times x minus a. So find what you need. First thing I notice is that I always go ahead and find my f of a first. So what is f of pi over 6? That would be the sine of pi over 6, which is 1/2. Then I've got to find a derivative. So back over here to the right, f prime of x, a little bit easier this time. The derivative of sine is cosine. So when I go to find the derivative at the same number, f prime of pi over 6 would be the cosine of pi over 6, which is the square root of 3 over 2. Now I know enough to plug my numbers in, so I can say that L of x is equal to my f of a value, which is the 1/2, plus f prime of a, which is root 3 over 2, times x minus my a value, which is pi over 6. It didn't ask us to approximate anything, so on problems like this, like I mentioned, this is kind of like your quiz, you're done. That's all it takes is to find a linearization of a function. All right, let's do another one. Let's go back to that square root idea, but this time I'm not going to make you approximate anything. So example number 3, find the linearization of the function f of x equals the square root of x at a equals 4. So kind of the same idea. L of x is going to be f of a plus f prime of a times x minus a. So once again, jumping to the first thing I always do is I find my f of a value, which is f of 4. This would be the square root of 4, which is just 2. I do need the derivative. So since f of x is equal to the square root of x, which is the same thing as x to the 1/2, I'm going to find my derivative by using the power rule. That would be 1/2 x to the negative 1/2, which is the same thing as 1 over 2 x to the 1/2, which is 1 over 2 times the square root of x. I'm going to take the same a value of 4, but now I'm going to plug it into this derivative. That would be 1 over 2 times the square root of 4, which comes out to be 1/4. Therefore, I can now find my linearization of the function. I can say that L of x is equal to 2 plus 1/4 times x minus 4. You can simplify all these if you would like to, but I am more than happy with you just stopping right there, especially on a topic that doesn't make a big deal going forward. But there you go. That's the linearization of this function. All right, so to wrap up this sorry, to move on, before I move on to the last topic, let me show you probably the one that people miss the most, not only the L of x part, but also I want to show you one more where you can do the decimals. So find the linearization of the function at a equals 0 of f of x equals the square root of 1 minus x, and then use this to approximate the square root of 0.9. So I've written it down a few times, but I'm going to keep writing it down since we're learning for the first time right now. So L of x is equal to f of a plus f prime of a times x minus a. Once again, I'm going to knock out the easy part first. At least I assume it's the easy part. I want to know f of a, which is f of 0. That is the square root of 1 minus 0, which is the square root of 1, which is 1. Kind of like the last problem, I'm going to say that f of x, since that is equal to the square root of 1 minus x, and I need to take the derivative of that, I'm going to rewrite this as 1 minus x to the 1/2. Now here's the part that I've seen students mess up because they're going too quick. This is technically a chain rule, so when you do the derivative, it is 1/2 times 1 minus x to the negative 1/2, and here's the part students always forget. They just assume the inside is 1 because they see an x, but the derivative of the inside is actually negative 1 because it is a negative x, and that plays a big factor in your final answer. So this is now the same thing as negative 1/2 times 1 minus x to the negative 1/2, and it cleans up now the same way. It's negative 1 over 2 times 1 minus x to the 1/2, which is equal to negative 1 over 2 times the square root of 1 minus x. Plug your a into that, so f prime of 0 is going to be negative 1 over 2 times the square root of 1 minus 0. So for the first time, we see that f prime of a can sometimes come out to be a negative number. All right, so now you can write your L of x function. L of x is going to equal 1 minus 1/2 times x minus 0, and that 0 plays no role in this problem, so actually this is the same thing as 1 minus 1/2 of x. Now for one more time, let me remind you, how do you approximate this? What we're trying to say is that where is the square root of 1 minus x equal to the square root of 0.9? That means that I need 1 minus x to equal 0.9. If I subtract the 1 over, 0.9 minus 1 is negative 0.1, and then dividing both sides by a negative 1 means that x is 0.1. That's the number you're going to plug into this problem. So I can say that L of 0.1 is 1 minus 1/2 of 0.1, which is equal to 1 minus, and 1/2 of 0.1 is 0.05. So this is going to end up equaling 0.95. And that is the approximate value of the square root of 9. All right, and last but not least, so this topic normally I probably wouldn't teach because it really, I'm gonna tell you, this idea has no bearing on anything we do in this class, but I know that some of y'all have to go on to Calculus 2 next. So in Calculus 2, there's an idea called differentials that they expect you to already know. So I'm gonna run through this really quick. I'm not gonna spend a lot of time on it, but I want you to see it at least in this video. So differentials say if y equals f of x, where f is a differentiable function, then we can define the differential dx as the independent variable, and then therefore the actual differential dy is defined by dy equals f prime of x dx. Now, where does this formula come from? Well, we actually saw it a little bit earlier. Remember when we talked about that there are 3 different ways that I would define derivatives? Well, let's use the second 2. If I know that f prime of x and dy dx are the same thing, there's going to be times, like I said, for those going to Cal 2, are going to need to get that dy by itself. So if I multiply both sides by dx, you can see that we can define dy as equaling the derivative of f prime of x times dx as well. And then from there, you can plug numbers in and you can evaluate your differential, and we're going to see that on the next slide. So last but not least, to wrap this video up, here is example number 5. I want you to find the differential y, and then I want you to evaluate dy for the given values. So example A, if y is equal to tangent of x, and x is pi over 4, and dx is negative 0.1, what is the differential and what is its value? So here's the easiest way to do this. When you're finding a differential, all I do is I take the derivative of y, which we're now going to call dy, not dy dx, so just call it dy. Take the derivative of tangent, or whatever the function is, in this case that's secant squared, and we're going to stick the dx on the right, kind of like the implicit stuff we've been doing in the last few videos. That's it. That's problem number 1. I'm sorry, that's part 1 of example 1. That is your differential. Now you're going to plug numbers in. So we can say that dy is the secant squared of pi over 4 times a negative 0.1. So that would be, so we have to square secant of pi over 4. So secant of pi over 4 is root 2. So that would be root 2 times root 2 is 2. And then 2 times a negative 0.1 makes this a negative 0.2. And that's your answer. In Cal 2, for those going on, this is the more important part, but there are a few rare times you will have to evaluate, so just don't fret when you're asked to do that. All right, and just one more so you have it in your notes that you're taking. If y is the square root of 3 plus x squared, x is 1 and dx is negative 0.1 again, what is the differential and what is the value? Now this one I'm actually going to have to rewrite a little bit because I'm going to have to do the chain rule again. I need to write this as 3 plus x squared to the 1/2 just to make this next part easier. So I can now say that the derivative of y is dy. This derivative is the chain rule, so that would be 1/2 times 3 plus x squared to the negative 1/2 times the derivative of the inside, which is 2x. Taking the 1/2 and the 2x and putting those together, I can say that dy is x times 3 plus x squared to the negative 1/2. And then if I bring that back to the bottom, I can say that dy is x over 3 plus x squared to the 1/2. And I know I have not forgotten that extra term. I'm coming back to it. Dy is x over the square root of 3 plus x squared. And while I didn't put it on every single step, I usually just wait to the very end to add it on there. Don't forget your dx term. This is your differential. And now to evaluate that, plug in what you know. I know that dy is going to equal 1 over the square root of 3 plus 1 squared times the negative 0.1, which is equal to 1 over the square root of 4 is 2 times negative 0.1, and negative 0.1 times 1/2 is going to end up being negative 0.05. This is the value of your differential. And that wraps up section 2.9. That also wraps up chapter 2. So in this video, remember we talked about, for the most part, related rates. So how do you solve word problems when you're solving for rates of change, when you're given other rates of change in values. And then we quickly looked over the idea of what linearization was. And then we kind of also quickly looked over the idea of differentials. In the next video, we're going to start chapter 3, which is the last chapter of material in this class. So we're going to start getting into the idea of graphing. So a lot of chapter 3 is all about graphing. So be ready for that in the next video.